All right, so I guess we're recording our second video of these papers that we started doing last week, and this is definitely exciting for me to talk about this paper with Leo Leo Barkley. Leo, you want to just kind of maybe introduce yourself as to who you are and
Yeah,
yeah, and how we met, maybe?
yeah. How we met, I think, was in 2015,
Yeah, that's right. I think so.
2015 reinforced concrete
That's right.
class. And I graduated from NC State undergraduate in 2016 and then did my master's with Mervin as my advisor. Graduated in 2018, did studies on reinforced concrete columns, reinforced with high strength steel, and then what we're going to talk about, kind of spawned out of that study. So graduated in 2018. I've been working as a consulting structural engineer for a company called Kinley Horn ever since. Yeah.
Yeah. No, I remember that class, that reinforced concrete class, and we used to do those little problems in class. I still do those where you do like little, example problems, calculate the flexural strength, and you're always like sit there and did it like in 3 seconds. It's like, okay, this guy knows what he's doing. I think to me this is interesting, this story, because in my mind, it's kind of the story of the unexpected. And you know how sometimes you start with these, not that we're doing any Hollywood productions here, but you start with these, you see these movies or TV shows, and you end up with the end result, and then they go back in time. Well, this is where it ended. It ended in the publication of the paper in the ACI Materials journal, which it first showed up on the cover of the journal when it was published, which was surprising to me, and then we got the really good news that it had been selected for the Wason Medal for materials research, and I think it was 2020 or 2020, 2021, which was surprising to me. I don't know how you felt about it, but
Definitely surprising to
definitely
me.
surprised. Like, oh my goodness, this is pretty amazing. So as a second video, I thought this would be pretty good because of this story of the unexpected. And I was thinking the other day how when we talk with all of our students, we always encourage people to kind of go beyond what the project entails, right? So there's always research projects, and they always got to do something, and it's important. And the deliverable for that project might be you have to do A, B, C, and D, things that are important for that sponsor, and we do those things. But if you kind of free your mind a bit and kind of open yourself up to opportunities of other things you can discover, you can really get to some interesting things. And this is just an example of that. So if there are any students who are watching this and you're all working in your research projects, wherever they may be, and you're doing great stuff, think about what are the things you could get from that. What are the things can you do? Open your mind to other possibilities, and that's really one reason why I wanted to talk about this. So Leo and I are going to have a little just discussion about this, and the idea being that if you're interested, to give you a bit of background on this particular paper and the test that Leo developed, that you can look at in the paper. Of course, ask us questions if you like. So just to give you a little bit of the background before we get into how we got to the BBT test in this paper. Back in 2014, I had the good fortune to have my first project funded by Caltrans on the study of high strength reinforcing steel. And it was a pretty straightforward research project. It was straightforward in the sense of what they wanted was straightforward. The execution of it was not straightforward. And a student who did that, David Overby, I think he's still working with you, right? So we got to maybe have.
Sits about 10 feet away from
Says
me.
10 feet away from you. So David would be a good person to have on a future topic, a future paper, because it was, well, at first glance, it looks like we're just doing a bunch of tension tests. Yeah, but it was a major effort. And he, in the conduct of that test, did 800 approximately tension tests to get the stress strain curve of A706 grade 80 steel. So in the US, 706 is a designation for weldable steel or seismic steel. And we came up with the recommendations that led to changes in this Caltrans seismic design criteria. So things related to strain and maximum stress, yield stress, ultimate stress, all the typical parameters that you would need. And they were expressed statistically. So there was variation, of course, with bar size for all these different parameters, including the strain and max stress, so the ultimate tensile strain. That's one that was lower than what you'd expect for grade 60 steel, but we felt good enough. It was high enough. It was sufficient that there was promise to use this in seismic design of bridges. And that led to our second project, which was a couple of years later, where we wrote a research proposal to study the behavior of columns reinforced with high-strength steel. And thinking about what the deliverables of that project were, we had to look at the performance of the columns, compare them to columns reinforced with grade 60 steel, look at plastic hinge lengths and energy dissipation and strain limit states. And we did that, and Leo did that, and we wrote a different paper on that topic. And we had instrumentation, which was this, we call OptiTrack. It's an OptiTrack system, which uses LEDs to measure position to a very high degree of accuracy up and down the reinforcing steel. And they were there for strain. That was, to that point in time, that's all we were using these things for, was to measure really strains and then curvatures. And we've been doing that for many years prior to that. And we did 4-column tests at that time, and we varied, reinforcing steel ratio and transverse steel ratio, axial ratio, to try and get a cross section of different design parameters. And those tests, the force displacement responses were shown here, and you can see, the behavior of the red is the grade 60 columns, or the companion columns, and black was the tests that Leo did, the ones with the high strength steel. And we noticed that overall, as you'd maybe expect, a slight reduction in displacement capacity, nothing drastic, but there was a reduction that was important to quantify. But the other thing that we noticed, is I think was more important, was over here, where we started seeing that in the case of the columns reinforced with the grade 80 steel, there was not a lot of delay between buckling and fracture. It was almost like the next cycle, whereas in the grade 60 steel, we'd always seen this multiple cycles in between, and we thought that was important and interesting. Is that, well, what's going on? Why is that different? And that's what led to this, right? So I don't know, Leo, if you want to chat a little bit about this, not to put him on the spot. But
yeah. Well, I'll say maybe for a future when you got to call up Chad. Chad did a bunch of those tests, so it was direct comparison between grade 60 and grade 80. And I think when we were thinking about it, right, Chad developed a bunch of different equations for developing, well, where does the cage or the spirals yield, and then what yields to then bar buckling in terms of trying to get different limit states. And bar buckling was always, you kind of bar buckles, and that's where you design to, and then you have a little bit of factor of safety after that. But I think after seeing, well, bar buckling, you don't really have a whole lot of factor of safety after bar buckling with the grade 80 column. So there was what's the difference? Why is there this difference? And so in reviewing it, this paper on the right was from back in 1993, I think, and really identifying that when a bar buckles, they did a kind of a cross section through this. We see, well, there are kind of these micro cracks that occur at the base of the ribs. So I think the thought was, well, maybe there's something in the terms of the actual. They called it in this paper, and we ended up calling it as well, compression strain that's related to how the tensile strength is affected. So we said, well, when it buckles, this was a long time ago, so I'd have to go back in the Wayback Machine, but basically taking the curvature and then using that curvature along the cross-section to calculate the strain, particularly the strain that it undergoes in the buckled bar would undergo in compression. So the compression strain on a buckled bar, which we were in the position to measure because of the OptiTrack system, which I guess we covered later.
Yeah, so that was really like the buckling induced bending strain. So that's one thing we hadn't really thought about, is when you have bar buckling, of course, the bar is bending, and that imposes strains along the cross section, and that, as you said, that strain on the compressive side, which Jose Restrepo suggested many years ago might be important, is something we kind of keyed in on and saying, okay, we need to look at what's the bending strain that you generate in a buckled bar. So then this is what you were getting at, Leo, with the OptiTrack, right? You go from
so position of the bar, which is what we had used it, as the position between the bars increases, that's how we would measure strain just linearly along the cross section. Right. And then you can really tell when the strains went off the chart when the bar had buckled, because then it is way off the chart. And that's what we used to say, okay, now the bar is buckled. Now we basically just say the bar is buckled. Let's ignore it at this point. But we said, well, actually, we have more data that we could actually use, and this is more fitting aligned to the position data there. So if you take the position data, do some calculus, which in this consulting world we haven't done in a while, but do some math to actually work out what the curvature is, and then use that curvature to then calculate strain, which we were able to do because we already had the columns and all the position data along the length of the buckled bar.
I think what's interesting too is you can see it, right? This is that position data you're talking about, and you can see at the bottom, you can visibly notice the buckled shape, and that's what's blown up in here. And that to take the second derivative of that display shape, and you get the curvature. And then of course, once you've got curvature, it's a bit obscured by our photo there. You take that and multiply it by the neutral axis depth over, and you get the strain. So it was kind of an obvious thing to calculate in retrospect, but at the time it was kind of like piece by piece. As I remember that we had this. Okay, we can get to this next step from that.
Yeah.
And you did though. So the ones on the left were. So we were referring to Chad. Chad refers to Chad Goodnight as a former PhD student who's also known in the consulting world. But he did many column tests to look at performance limit states for conventionally reinforced concrete bridge columns. And we had this wealth of data available that Chad had used for many different things. But now we have this ability to go back in time and say, okay, we have this data from 10 years, approximately, not quite 10 at that time, it had been maybe 7, 8 years prior, and we could look at that information, look at that shape, look at that buckled shape, look at the display shape, calculate the curvature, and then calculate the corresponding bending strains. And that's what we did with Chad's data, and it was really quite interesting because if you look at any one of these bars that you see here, bar 0 to 25 or 30, those are different bars and different tests. It doesn't really matter which one it comes from. But if you take any one of these, for example, if you looked at, let's say, the one is number, pick a good one here, maybe like number 8. So if you look at bar number 8, all these little squares, what they're showing is that after loading to that level of displacement in that column, and then going back in the other direction, that particular bar was being subjected to bending, but it didn't fracture. It only fractured once it got to one of these X's. So as you can see from that one in particular, you could bend the bar quite a bit until you got to a point where you couldn't. And at that point, upon reversal, that bar had fractured in that column. So what we did was to say, okay, let's look at all this data and find out where is the value of the lowest X, the lowest fracture. Well, that was right around 13%. What's the value of the highest unfractured bar? That was about 16%. So what we inferred from that was that the bending strain, the critical bending strain that you can sustain for grade 60 steel is somewhere between 13 and 16% before the bar fractures. And then Leo, you did that for your tests. And
yeah, so like we mentioned before, we saw that there was one of the bar buckled in the grade 60 tests, the conventionally reinforced. It had a couple different displacement cycles, and we're trying to look at why this happens. So we did the same thing with the grade 80 columns, and again, there's only I think there were 16 bars in each of these tests. Right. So you only had a couple bars on the extreme fibers that are actually buckling, which is why you don't have a vast wealth of data. We just have the data that we have from the bars that actually buckled. But in the grade 80 columns, the bar begins to buckle, and that's really when you can when the bar first kind of slightly buckles is when you start to be able to measure bending strain. For the rest of the test, the bar is straight, you assume there's no bending strain at all. But we saw in these grade 80 bars that when they kind of buckled once, came back, and then they were fracturing the cycle after a much lower bending strain. So it would be subjected to this bending strain that's seen here. So like the X on the first column is around 12%, and then there were some other ones that we continued to look at. So around between 9, 10, maybe up to 11, they would be subjected to that bending strain, and then on the next cycle they would fracture. And I think at this point it was also a typical bar that fractures, if you subject it to tension, right, it's going to have necking, and there's going to be you're going to have a clear, and I'm not sure how this is going to actually align. So I tried to take these are from way back in the day. So you have a bar, I'll just put it against my shirt, right? So you take a bar, it necks, and then it fractures, and there's a very uniform cross section kind of across this. But what we saw, and looking back at the pictures of Chad Goodnight's tests, and then from our tests, the bars that had buckled and then fractured did not experience necking. They basically went from the entire cross section. I'm not really sure if that's going to show up that well, but there's no necking at all. And then the cross section itself, I think there's pictures of this in the actual papers themselves, but the cross section looked much different. So we thought there's some sort of different behavior that's going on. So when we noticed that there was a difference between the grade 60 and the grade 80, we said, well, how can we recreate this without taking whatever it was, a year to build more column tests? We want to recreate this situation where we have a bar that goes from buckled and then gets subjected to tensile load. So we said, how do we recreate this system?
Exactly.
And so using the MTS machine we basically just said, well, why don't we just put one single bar in? We can vary the parameters, we can vary the diameter of the bar, the length, the unconstrained, constrained length L there, subjected to a
length between the grips.
Subjected to a compression load and then a tension load. And so we found that if the bar was subjected to a high enough degree of curvature, then the bar would fracture brittly along the next one. So, sorry, you go back. One, so like the...
Maybe not. Can we go back one? Doesn't like we can with this one.
Oh. Well, so
one direction.
So the brittle. This would be theoretically more elastic. It wouldn't be as brittle of a fracture. So coming down here, subjecting it to a compression force, compressive strain, comes up, and if the bar fractured here, without being able to actually go into yielding or the typical where you would typically see a bar extend to elongation wise, that would be more brittle. Here you'd be more elastic.
More ductile, yeah. So you've got the exactly. So the amount of bending you subject to the bar to, the more bending strain. If you bend it enough, you get a brittle fracture. If you bend it only a little bit, you're below that critical bending strain. It's ductile. I think coming up, we've got some slides and they show it, but this was your setup, right, where you had the bar between the machine heads, and you had and of course in this case now you have the opportunity to put many markers, right? There's like 7, 8, 9 markers on there.
Yeah.
As opposed to only the 3 of the column. The column, you're lucky to have a few markers to measure the curvature. Here you've got enough that you can get the entire display shape pretty accurately. I think this is actually I think this graph would probably show what you were suggesting there, Leo, right? Because this one's showing bending to a particular level of bending strain that allows you to get significant elongation. As you can see, it kind of progress through, and eventually bar fracture. This is. I think this is exactly the graph you were talking about earlier.
So going so the green obviously is not subjected to as much. It does buckle because the force doesn't continue to increase as the bar buckled. So the green bar has buckled to some level, but it hasn't buckled to an extreme level where when the reloading was reversed, the green bar was able to be a ductile failure. Like you saw on the previous slide, there you experienced necking. You had a much higher ductal failure versus subjected to just slightly higher curvature, the red, we saw a brittle fracture.
So that distinction tells us that that critical bending strain is somewhere between those two values.
Yeah, so that would be the
ductile.
You see necking. I guess I didn't mean to bring my little guys. And this is more brittle, right? So there's not a lot of necking, and you can see all of the. I'm not a metallurgist, but basically it looks like there's an explosion coming from like the top half of here. This is the kind of the inside point of the buckle where the compressive force is the highest, and that's what we were really looking for to see. Well, where is this critical bending strain that then resulted in the ductile or the brittle fracture?
Exactly. Yeah, I think this was also interesting because this shows this nice progression that you were talking about, Leo, because you have, all these individual tests had been buckled. So they were all buckled and then pulled to fracture in tension. But several of these early bars, they were able to recover that buckled shape and fail in a ductile manner. Whereas the ones in the right, this is an extreme case, this one had been subjected to such a high level of bending strain that when you went back in reversal, it just immediately fractures. Yeah, and I think we kind of divided those as, sort of the more ductile failures and then the more brittle ones.
Mm-hmm.
And then there's, of course, this graph, which I remember when you were looking at this. I remember going into your office and seeing at one point when you had this information, and it to me was just pretty amazing that this worked out the way it did. So this is your bending strain graph, which is, I think, pretty cool.
Yeah, so we tried to correlate. I think this is off of the actual column data.
Yeah. So these were the blocks were from your column data. So this is the grade 80. These were your columns, and this is Chad's columns, right?
Yeah.
Yeah. These were from your material tests.
Yeah.
Yeah. So you could see that it really correlated well, right? I mean, this was from your material tests. You were thinking that we were hoping that it would line up, and it actually did. So here you can see where it drops where the cursor is. You can see that you're getting about to a level of about 10% critical bending strain, and then it just becomes brittle. So right around this point, and that's very close to what Leo you were seeing in your columns. And then for Chad's test, you see it's ductile, the air is brittle down there, and the transition somewhere in there. So it's a little bit to this, let's say, to the higher side of that purple or that reddish band is where that's matching up. But that we could get it to match up that way was quite interesting.
The buckle bar tension test
Exactly.
on the MTS machine was able to replicate the behavior of the columns, which then led us to think, well, this is the actual behavior of the buckled bar. It's not getting to its actual critical strain for elongation and then fracturing ductily. It's really getting to this. It's buckling, and that buckling is taking it to this other limit state, which isn't just the limit state you get to with a pure tension.
Exactly.
Buckle limit state.
Mm-hmm. Yeah, and I think we once we had some confidence in it, we then applied that test to the microalloy steel that you'd used in your test, Leo, and then we'd also applied it to a second batch of microalloy steel as well as some quench and self-tempered steel. So at this point in the research, we were all interested in differences between quench and self-tempered steel and microalloyed steel, and are there differences in behavior? And to complicate things, I remember we were looking at this, and you looked at the ribs for these two mills. So these were both microalloy, but the second mill had these deformations which were much smoother, right? I mean, you can see it there. The radius was much softer. And the hypothesis was, will these behave the same? Because if you look at this, the second mill seems like it might have a bit less strain concentration, whereas mill 1 has a sharper radius, maybe higher strain concentration. Might that lead to a lower bending strain? And then you saw that in these tests. So you could see it in mill 1.
So mill 1, I think, was the one that we did the column test
exactly,
with.
Yeah.
And we thought, well, what influences this bending strain? Mm-hmm. Is it the actual metallurgy of it? Is it quench and self-temper? Is it microalloyed? Or is this, these geometry of the actual ribs?
Or some combination.
Or some combination of the two, which is probably some combination of the two. Mm-hmm. And what we saw, the blue is the one with the much higher radius at the base of the rib, because if you go back to that Restrepo image with the micro crack at the base of the rib, you think if that's subjected to compression, a more refined stress concentration would lead to more of those cracks, and that's what we saw when we ran these through the buckle bar tension test.
So it made quite a difference, right? The bending strain capacity increased to 16, 17, 18%, and both of these are grade 80 steel. And then the quench and self-tempered steel, the process, not maybe we need to get into it now, but the process was different in terms of how it's produced, not by microalloying or adding different small alloying elements, but rather by a manufacturing process that leads to, you saw a different behavior in the BBT test, right? You could see this, the black was the microalloy and the blue was quench and self-temper, so it was much
more gradual, not as but a bit of a drop off.
Exactly. It wasn't such an abrupt change. And that led us to, not to say, we always are mindful of, there's many different ways to produce steel and there's not a right or wrong way, but you get different behaviors, and this could be interesting sort of behavior that could be beneficial. Then you did these are interesting.
Well, I think we took that, we saw, there's the lower stress concentrations. Those bars did better in the buckled bar tension test, and so the critical bending strain was higher. So we thought, well, what if there's no stress concentrations at all? So we sent this is an actual rebar, which we just sent. I think it was at NC State, the machine shop.
Exactly.
We just had to mill the ribs right off the bar and saw, well, what is the critical bending strain with these bars with no ribs at all? And we saw that, so this was, again, the black, same bars that we ran in the column test with the lower critical bending strain. The red was the lower or the higher radius, so
lower strain concentration.
Lower strain concentration. But then as we go out here, this red dots are
hollow ones,
the same ones, but with no ribs on them, and so it significantly increased the critical bending strain. So I think it was just a, looking
confirmation of what we thought would be the case.
Confirmation and just running through, like you said, running through different options, saying, well, what's going to influence this? We see this, we come from these columns, and we go to this test on just a bar, and then there's almost unlimited possibilities. You continue to study and continue to look at them.
And Leo, when we were chatting yesterday, and you reminded me that we then went to California at one point during the research to Caltrans to present them the work, and I think it was right around here, and I think we showed them this, and they got excited about, well, maybe we should go back to smooth bars, and we said, well, this is true, but of course you need that deformations for bond. There's ways around it. We actually did pursue that. That's the topic for another day, but we did have done some tests with machine bars in the plastic engine. There's a good and bad sides to it, but for sure you get this increased bending strain capacity. So we didn't want to go too far on this because this test has been used a lot. We use it a lot at NC State, and other people are now using it as well. And we've got students here who are using it to do tests on low temperature effects. So Lena is one of our PhD students, and she's built a little environmental chamber and is doing BBT tests at -40 to see how the temperature affects that. That's pretty neat. And we have another student studying corrosion, and he's looking at the effects of, this is David Komanichu, and he's looking at how the pits from corrosion, they are strain concentrations, right? So he's looking to see, can you correlate bars that have corrosion using the BBT test. So it's kind of gotten a life of its own. It's a really quite useful test to kind of evaluate at the material level. So that was kind of our story, but I don't know. To me, it was really kind of a neat thing to go through, and very rewarding in the sense that we, I think, discovered something that you can see had some future applications to it, and we've prepared a document for Caltrans that simplifies the test, because the way we do the test needs an optical system, but there are ways around it if you don't have that, to kind of get an approximation to it, where other labs could be able to do that. So I think it's been a good experience. So we wanted just to share that with everyone, and if people are interested, you can reach out. And anything else you wanted to add on your experiences, and how is your consulting practices going well, and you're happy, and working on lots of interesting, you're doing mainly building design, right?
After studying lots of bridges and masters, now doing a lot of building stuff.
Now you got experiences in both. And mainly structures in the area. You're doing buildings outside the local area.
Mainly the southeast. A little bit of this.
Anything with high strength steel in the building practice yet, or how's that going?
We haven't, and not a whole lot, but I mean we're also in the southeast.
Exactly.
So we'll see when it comes over from the west coast and.
Well, it's made its way into ACI code, so it's a step in that direction.
Okay.
Well,
I mean, I'll say just for you, and thank you for pulling me in to do this. But this is not be possible without you and your mentorship and guidance. So really appreciate that.
Well, it's also thank you, Leo, and I think that it's having great students that matters. And you were exceptional, and we had a lot of great students over the years, and that's led to a lot of good work. So we'll share more stuff in the future. We'll get David Overby, your office mate, to talk about. We'll have to go back in time a little bit further and for him to talk about his work and kind of go from there. So, all right, and we're happy to hear any comments from anybody. If you like this format, we're a little more casual, and go from there. Thank you all.